The next unit we're going to be taking a look at is trigonometry. So, for trigonometry, from the Greek word trigonon, three angles, and metro, being measure, is a branch of mathematics dealing with angles, triangles, and trigonometric functions such as sine, cosine, and tangent, or sin, cos, and tan that you probably see on your calculator but you might not have used in the past. In this unit, we're going to study the relationships between the sides and angles in specifically right angle triangles. Once we get to grade 11 and 12, we're going to focus more on non-right angle triangles, or the extensions of trigonometry and how it works once we are getting into calculus. So first, the diagram shows a series of similar right triangles starting at the origin in A1 and B1, and then the origin in A2 and B2. It wants us to complete the work using a ruler to measure the indicated sides to one decimal place. Well, I'm not going to assume that you have a ruler readily available, so I'm just going to tell you. So, for the first one, it tells us that it's going to be 1.4 centimeters divided by 2 centimeters. For the second one, it's going to be 2.8 centimeters divided by 4 centimeters, which is going to give you 0.7. For the next one, it's going to be 4.2 centimeters divided by 6 centimeters, which is going to be 0.7. And for the last one, it's going to be 5.6 centimeters divided by 8 centimeters, which is going to give you 0.7. Amusingly enough, this is just going to be the opposite divided by what we're going to call the adjacent side length. And in all these cases, like with the graphing unit that we just did, it's realistically solving for what the ratio is of the vertical change to the horizontal change in this case. So it's literally just telling us a slope, which is why we know it's always going to be the same. All based on this right angle triangle. So we can say that the ratio is going to be 0.7, and it's somehow connected to an angle of 35 degrees. In the second case, we have a new angle of 58 degrees, and I'm going to tell you what these measurements are again. So we have, for the first one, 2.4 over 1.5. For the second one, we have 4.8 over 3, which is also going to be 1.6. For the third one, we're going to have 7.2 divided by 4.5, which is also going to be 1.6 when I divide them. And lastly, 9.6 divided by 6, which conveniently enough is once again 1.6. So we can conclude that the ratio of 1.6 is somehow related to the angle of 58 degrees. So when we're talking about the ratios of the sides of a right triangle, then we have this generic triangle where we have the origin here, we have points A and points B, and we know that it is a right angle triangle. If I'm looking at angle X, then each of the sides of the triangle is given a special name relative to the acute angle that I'm looking at. So in this case, it is based on, in a right angle triangle, looking at from the perspective of angle X. The longest side is the hypotenuse, which most of us already knew for a right angle triangle. The side opposite of X, which is the length of A to B, is called the opposite. This is the side length that is not used to create X, which is why we call it opposite from X. The third side is going to be called the adjacent. Adjacent meaning beside. So if I have the hypotenuse is the longest side, which is going to be one of the side lengths used to make X, the other side length that is used to create X is going to be called the adjacent. Remembering that this is always relative to the angle that I'm looking at. So if I look at example 1, and it wants us to state the hypotenuse, the opposite, and the adjacent. Well, one of them is never going to change. The longest side, no matter where x is, x being down here, is always going to be the hypotenuse. The other side length that touches x is always going to be the adjacent. And the side length that doesn't touch x is going to be called the opposite. If I look at the next example, it's moved where x is, but the rules still stay the same. The longest side is going to be the hypotenuse. The other side that touches x is going to be the adjacent. And the side that's opposite or doesn't touch x is called the opposite. The ratio of AB divided by OA in the diagram at the top of the page is the same ratio we used in the warm-up. This ratio is called the opposite divided by the adjacent, or the tangent ratio. So anytime we talk about a tangent ratio, we always mean the opposite side length divided by the adjacent side length. There's other possibilities as well. We can have the opposite divided by the hypotenuse is going to be the sine ratio, or the adjacent divided by the hypotenuse is going to be the cosine ratio. If I take the reciprocal of these, then we just call the reciprocal of sine cosecant. The reciprocal of cosine is secant, and the reciprocal of tan is cotangent. You're not going to use these until you get to grade 12. Before then, we're just looking at the basic ratios. We call them the primary ratios. The other ones are the reciprocal ratios. So we're just using the primary ratios for what we do right now. The simplified way of stating this is SOHCAHTOA. Sometimes you'll see it in these triangle forms. And all it means is sine of an angle is equal to the opposite over the hypotenuse, cos of an angle is equal to the adjacent over hypotenuse, and tan of an angle is equal to the opposite over the adjacent. Used in the diagrams in class example 1, complete the examples below. So if we're stating from example 1 that our side lengths are going to be represented by either the length of F to E, of F to D, or, sorry, here, let me highlight this, F to E, or the side length of F to D, or the side length of D to E. And I can do the same thing on this side, V to S, S to T, and V to T. Then those are my side lengths. I can state these side lengths in terms of what the ratios would be. So I'm going to say that, well, for my sine ratio in the first case, for A, if it's the opposite over the hypotenuse, I'm going to call the opposite side length DE divided by the hypotenuse E to F. Adjacent is going to be D to F divided by the hypotenuse E to F. And the tangent is going to be D to E, the opposite, divided by D to F, the adjacent. If I use the second triangle, then I'm going to say my sine ratio is going to be the opposite, S to V, divided by hypotenuse of T to V. Or the cosine is going to be my adjacent, s to t, divided by my hypotenuse, t to v. And my tan is going to be my opposite, s to v, divided by my adjacent, s to t. For the angle of 8 degrees in this diagram here, complete the work below to express the three primary trigonometric ratios as rational numbers and in decimal form to the nearest thousandth, or to the nearest 3 decimal points. Well, I'm going to state that for my sine ratio, I need to make sure that I know which side is going to be which. Well, the longest side is still going to be my hypotenuse. I'm going to have the side that touches it is going to be my adjacent, and the side that doesn't touch it is going to be my opposite. I can always label this just to make sure I'm putting the right numbers in the right spots. So I'm going to say if it's opposite over hypotenuse, that would be 20 over 29, which would equal 0.690 to the nearest thousandth. If I'm doing my cosine ratio, that's going to be my adjacent divided by my hypotenuse, which would equal 21 divided by 29, or 0.724. For my tangent, I'm going to state that this is going to be my opposite divided by my adjacent, which is going to equal 20 over 21, or 0.952. So I can always either express my ratios as a rational number, like we see, rational number or fraction like we see here, or I can represent it as a decimal form. Just remembering that in a lot of cases the decimal form will be a rounded value.